Imagine you are given a data set with only one feature. Easy to visualize, right? Now let's take it to 2 dimensions, 2 features. What about 3 features? It's still visualizable. But what if our data has more than 3 dimensions? A 4, 10 or 100 dimension, 100 feature data? It becomes impossible to visualize. The structure exists, but it is hidden. This is exactly the problem that Kohonen set out to solve. He proposed a simple structure, a regular 2D grid, a simple, regular, 2-dimensional lattice of nodes. This grid does not know anything about the data yet. There is no order, structure, or relationship to the data. Each node or neuron of the grid is associated with a weight vector with the same dimensions in the data space. Initially, these weight vectors are randomly arranged in the data space. The grid exists, but its representation is meaningless. Let's take a simpler grid to visualize the learning process. We introduce one data point at a time. We look at the adjacent nodes and ask a simple question. Which of these nodes is the closest? By computing the least possible Euclidean distance of the input from the weights, we can find the corresponding node or the neuron that best represents the input at the moment. This neuron is called the best matching unit or the winner. Once we find the best matching unit, we move it. We take its weight vector and shift it slightly towards the input. But here's where Kohonen's idea departs from simple clustering. We do not move just the winner, we also move its neighbors. Nodes that are nearby on the grid are also adjusted, though by a smaller amount. Nodes farther away are affected less or not at all. This influence is controlled by a neighborhood function, a smooth curve that decreases with distance on the grid. So a simple input does not just update one neuron, it pulls an entire region of the grid towards itself. If we repeat this process again and again for many data points, something remarkable begins to happen. At first, the movements are large. The grid is loose, unstructured, and flexible. Gradually, the learning slows down. The adjustments become smaller. The neighborhood shrinks. Global organization takes place. Now only nearby nodes move together, refining the structure that has already begun to form. This is the phase of fine-tuning. Over time, the weight vectors spread out across the data distribution. The grid, though still flat and regular in its own space, becomes embedded in the data space. It bends, stretches, and aligns itself with the underlying structure of the dataset, and most importantly, it does so while preserving neighborhood relationships. At the end of this process, we are left with something powerful, a 2-dimensional map. Each node on the grid corresponds to a vector in the original high-dimensional space. The grid itself becomes a representation of the data distribution, not just by projecting points down, but by organizing representative vectors into structured layout. Nodes that are close together on the grid end up representing similar data points. Nodes that are far apart represent dissimilar ones. The grid represents the data distribution, revealing its structure which was hidden from plain sight. Now let us see how we can interpret this map. The weight vectors appear as clusters in the data space. Boundaries emerge from distances, but what defines these boundaries? In the same cluster, the weight vectors are close to each other. Some neighbors may be close, but different from each other. What if we measure this everywhere? This is what a U matrix does. It calculates the average distance to the neighbors of a node and structured it in a matrix corresponding to the grid. If the value in the matrix is high, it means that the boundary was formed. The regions are clusters from the data space, and the boundaries together characterize the self-organized map. Now let's see how we can use the map to identify data points. Let's say we have a new observation. We find the best matching unit, map it to the grid. Whichever cluster it is mapped to, The cluster is the class of the given data. You can do this for different data points and different areas of the data space. The high dimensional data has successfully been converted into a 2D representation. The trained self-organizing map is now ready to classify new data points. Even without labels, the self-organizing map already achieves something profound. From disorder, we create structure. And this is the essence of Kohonen's idea. Not merely clustering, not merely dimensionality reduction, but self-organization, a system in which structure is not imposed explicitly but emerges naturally from local interactions. From simple rules applied repeatedly, a grid that begins as a blank slate becomes a meaningful map. A collection of independent vectors becomes an organized representation.